Hello and welcome back to Mathematics Tutorials. Today we're going to be talking about second derivatives and concavity and some of the things that second derivatives can tell us. So we're not going to be going over how to find the second derivative because I already went over how to find a derivative in a previous video and it's the exact same process. You're just doing it again. So if you want to, watch that video. But let's get right into it. So we have three functions here. We're going to call this red one f of x, and it turns out that the blue one is the derivative of the red one, and the green one is the derivative of the blue one. So this is basically uh, f prime of x, and then this is f double prime of x. So that means that this is our second derivative of this. So first thing you notice is that this is a x to the third function, this is an x squared function, this is an x function, which makes sense because in the past video we saw it goes down by 1 every time, right? So that's kind of the relationship, right? It goes down 1, goes down 2, and then of course if you had a third derivative, it would go down 3. So what is a derivative, right? Derivative is the slope, right? The slope at a point on this function. So if we look at, like, say, right here, it looks like the slope is about 0. This is about negative 0.6. So if we went over here and went to about negative 0.6, we would expect that it's about at 0, which makes sense. Similarly, if we go here, right, looks like a pretty strong positive slope to the left of negative 1. And if we go here to the left negative 1, it's pretty positive. The numerical value of the slope is pretty positive. So that checks out. So that tells us how the function is changing. But what if we want to know how the derivative of the function is changing, right? Basically the change in change, right? The double change, I guess. So for that, we would need a second derivative. So if we look, let's say from this point here to this point here, let's look at the slope, right? Slope is very positive, slightly less positive, slightly less positive, 0, slightly negative, more negative, more negative. So this whole region, right, from here all the way over to here, right, this whole region, the slope is decreasing, right, because it goes from very positive to slightly less positive to 0 to slightly negative to more negative, and that's in this region. So if we look at the first derivative, that actually is reflected. We see that it's going down, right? It's decreasing. It starts positive and it's going down. So if we look at the change in the change, we will kind of expect this to just be negative the whole time, right? This starts positive because the slope is positive, but it's decreasing. But the second derivative, you can see in this area, this is just, the line just extends, by the way, nothing tricky happening. You can see that this whole area, it's just negative because in this entire thing is just going down, right? Even though it starts positive, it's decreasing the whole time, and that's what this reflects. This being, less than 0 reflects that it's just decreasing this whole time, right? And if we look at from here, this is a special point right here where it changes, right? We go from being, somewhat negative to less negative to 0 to slightly positive to more positive, which means that from, 0 onward, right, this whole time over here, the slope is increasing, which means that the change in slope is positive, which means that the second derivative will be above 0, which it is, right? If you look at all this, and then that'll extend out that way. So this point right here is pretty important, right? And that is what they call a point of inflection, basically where it changes. This is called concavity, right? So if we have, so this is concave down. This is concave down, and this is concave up. And so what this means is basically just what I was saying earlier. If it's concave down, that means that the slope is decreasing, which means the second derivative is negative. So see how this looks. This part is concave down, right? This whole part right here, approximately, right? Which means that on the first derivative, it's decreasing, right? It can be anywhere. It can be entirely in, a positive quadrant, but it is decreasing, right here, which means that here it's negative. So this will not be in the positive quadrant at all. It is just decreasing, right? Or it's decreasing here, which means it's purely negative, right? So concave down basically just means the second derivative is negative. Concave up is the exact opposite, right? In this interval right here, we see that this is increasing, it's going up, like physically rising. And then here we see that the second derivative is positive. So concave up just simply means that the second derivative is positive. And so this is a point of inflection, or inflection point, and it changes concavity at this point. And these are very important. And the thing about these is that they're actually not very obvious. There's something like, if I said, where's the zero of this or where is the slope zero for this function, you'd be like, okay, obviously right there. But a lot of the times, it says like, where's the point of inflection? You know it's somewhere in here, in this kind of area. But see here, here, here. It's actually kind of hard. So what you would do is you would find the second derivative and then set that equal to zero. So I'll do a quick example. I think the exact formula I used for that one on Desmos was this. So if you expand that out, right, that'd be x squared. Uh, let's see. Oh, x squared minus 1 x. So that'd be x to the third minus x. So if you find the second derivative, right, that'd be 3x squared minus 1. And that would be 6x. So 6x equals 0. And of course, x equals 0. So I was right. The point of inflection is exactly at 0. So, but that's what you would do to find that point of inflection. Um, So yeah, the tricky thing is getting, the first, second, third, or not first, second, third, the first and second derivative sorted out in your head, right? Because concave down means that this is decreasing, but that doesn't necessarily mean that it's negative, right? But it means that the second derivative is negative, and you can even do like third derivative, fourth derivative, all that stuff. But that's like you wouldn't really encounter all that stuff. Um, yeah, so it's very important. Uh, Concave down simply means that the second derivative is literally like negative. The value is negative, not the slope. The slope obviously here is positive this whole way, right? It's linear. So the slope is the same the whole time, and the slope is positive, but the actual value itself is negative. Now, if you were given a graph of the first derivative, right, if you're given this, and you were told where is it concave down, you would look at where the slope itself is negative. So even though the slope is getting less negative, it's still negative for this entire interval. So if I were to say, here's f prime of x, where is f of x concave down, you would just see where is the slope negative. Same thing, positive, by the way, concave up. If I said, where's concave up, and I gave you this, you would look at, okay, so negative slope here, slope of 0, so it changes, and positive slope, so this whole thing right here, this whole right side. Um, Now if I gave you a slope of, or if I gave you a graph of the second derivative, it'd be pretty simple to find out where's concave up and concave down. Concave down is where it's negative, like the literal value, not the slope or anything, just the literal value is negative, and if the literal value is positive, then it is concave up. And of course, if it is at 0, then that is an inflection point if it's changing. Of course, if you see something like this where it touches 0, I don't believe that is an inflection point. Now, if I gave you the graph of f of x and ask where is concave up and down, you would look at this change in slope, right? Like I said earlier. So you would look at here, right? You'd be like, oh, okay, very positive, but it's decreasing, and then it is increasing here. So you would see somewhere around there it changes. So general rule of thumb, it kind of looks like a smiley face, or not smiley, but just like a smile. So concave up is like that, concave down is like that, smile and a frown. So if you have something like this, right, have something like that, in general, you're kind of thinking, okay, so it's probably concave down, and then it's probably concave up for a little bit, and then down for a little bit, then up for a little bit, then down for a little bit, then up for the rest of the way. Um, so it's kind of easy to just kind of intuitively see where it's concave up and down, at least sometimes, not always the case. But the hard part, yeah, is seeing, where it changes, because getting the exact values where it changes, because it's not always obvious. Sometimes it's a very gradual thing, which makes sense, right? If you imagine if this was the graph of the second derivative, and instead of like this, like ours, it was more like gradual of a change like that, it would be very hard um, to figure out, just based on looking at the graph. So I think that does it. It's a pretty simple concept. Um, Again, the main thing is just thinking about, what information do you get from a first derivative versus a second derivative versus the actual function, because they're all going to tell you different things. And you need to know what you're looking at and what you need to know about what you're looking at. Do I need to look at the slope? Do I need to look at the value? Do I need to look at change in slope? Stuff like that. Um, and it can be a lot to keep in your head, but I don't think it's too unbearable. Um, if you have any questions, leave them in the comments. Other than that, thanks for watching. Next week's topic, let's see. All right, so I just did concavity. Let's see, optimization problems, Newton's method. I don't know what any of this means, I'm not gonna lie. What is Newton's method? Do I use that? Is that important? Oh, is that one of those like approximation things? Probably, right? Yeah, basically. So I think we can go to antiderivatives. I don't think I have a video on that yet. If I do, then I'll change it. But for now, we'll go next time. Antiderivatives / indefinite integration. All right, so that'll be next time. Moving on from derivatives and entering the world of integrals and antiderivatives. So thanks for watching, and I will see you next time. Goodbye.